Okay, so I'm going to go through a PDE example today. All right, so to do this I'm going to use the method of separation of variables. And I remind you that this is a method that works for a homogeneous PDE with homogeneous boundary conditions. So the methodology consists of separating the variables. You plug in, you rearrange so that I get a function of one variable. Let's say I have u of x and t. Then I need a function of x is equal to a function of t. That can only be true if I make these equal to a separation constant. That means that my PDE becomes two ODEs. You solve the ODEs. After that, I apply the simple extra conditions, and usually these are the boundary conditions, or the relatively simple boundary conditions, and from that you find what basically the separation constant is, which we'll call lambda. So applying the extra conditions, it will constrain the functions here. So when I separate, I, for example, put big X of x, big T of t. I constrain these and I find the lambdas when I apply the simple extra conditions. I formulate the general solution. That's got a bunch of arbitrary constants in. And then I apply the final more complicated condition. And the goal there is basically to choose these arbitrary constants in the general solution so that you end up with a nice solution to the whole problem. So that's what you do for a homogeneous PDE with boundary conditions. And along the way, when we get down to here, that's where we have to use some features of Fourier series. So let's just talk about that. Here we've got the Fourier series. And if f of x is f of x plus 2l, that means it's 2l periodic, then I can use the Fourier series theorem, which tells me I can express my function as a constant that we always call 1/2 a0 plus a sum, and we have an an cosine of n pi x over L plus another sum of a bn with a sine of n pi x over L. And when we build this Fourier series, we need to be able to calculate the coefficients, and they follow from various integrals. So that's a0, an, looks the same except there's a cosine in there, and the bn is the same sort of an integral except that I have a sine in there. And what I've done here is I've written down the general formulae for arbitrary periods. So my period is twice big L, and as a result of that, the cosines and the sines, they have this argument which is n pi x over big L, and I'm integrating from minus L to big L, and I'm dividing by this half period, big L. Right, so that's the Fourier series. This is the separation of variables problem. Now, when I employ this technology of Fourier series, when I import it into this particular problem, it's because I've got a general solution down there which is somehow a Fourier series. It's usually not the whole Fourier series, it's usually either a Fourier cosine series, so it doesn't have this bit, or it's a Fourier sine series, so it doesn't have that bit. Now, that is the connection between here and here. There are two parts of the Fourier series theory that we really need when we go from the general solution here to applying the final complicated extra condition. Because what we usually need to do is we usually need to take the series, which is some part of this, and make it equal to some given initial or boundary condition. That's the final complicated extra condition that we've given, right? So we have a prescribed function that we've got to fit. We're going to make sure the general solution equals it on the boundary or at the initial time, and that requires us to pick these coefficients. So the two bits of the Fourier series theory that we really use are, one is really the justification of how, in this problem over here, we can take this seemingly arbitrary initial or boundary condition and represent it in the way that we need to do. Right? So there's a sort of a proof of concept that comes in that we have to go through. That's a sort of largely a technical detail because it's just justifying how we can do this. The second part, which is the more important part, are the formulae for the coefficients. This series is essentially useless unless we have these formulae for the coefficients. So given our prescribed function, we need to know how to get the coefficients. So that's really the more important second part of the connection between the Fourier series theory and our separation of variables approach. Okay, right, so now I want to solve a particular problem. I'm going to be using this particular technology. One of the issues, however, is that I'd like to apply it to a slightly more complicated problem. I want to grapple with an inhomogeneous PDE and with inhomogeneous boundary conditions. And in that situation, I have to take a first initial preparation step in order to get through separation of variables. So let's add on a step at the top here. And the step that I need is to first of all get what you might call the steady state solution. That solves the time-independent problem. So this is step 0. Oh, that's the wrong pen. So this is step 0. Let's change colour. I've gone from lurid pink, and now I'm going to go to lurid green. Okay, so what's step 0? So I have an inhomogeneous problem now. That means that there are extra terms in the PDE. And there are extra terms in the boundary conditions, so that the boundary conditions look something like u or u derivatives equals something. So the homogeneous problem that this all applies to, it doesn't have these extra terms in the PDE, and it just says that u or the derivatives of u is 0. Okay. So what we first of all need to do in order to prepare the way for this is to find the steady state solution. So that means it's independent of time, so let's call it big U of x, and it satisfies the inhomogeneous differential equation and boundary conditions. And once we have that, we can sort of go through this thing again. There's a slight difference, however, which is that I have to split the solution up into two parts. So I then put u, which depends upon x and t, is equal to big U of x plus v of x and t. Because this thing satisfies the equation and the boundary conditions with these extra terms, the v here satisfies the equation and the boundary conditions without them, and so the v satisfies the homogeneous problem. And because of that, I can apply all of this strategy to v. So at this point, I separate variables here. And I follow this strategy, not for u, but for v. And that's the way it works when you have an inhomogeneous problem. So that's the background. Let's now look at the specific problem. So in order to do that, I'm just going to save some of this. So there's going to be some technology of the Fourier series that I need. And I'm going to actually use only part of this. If I have f being even, if f is even, then a constant is even and a cosine is even, but a sine is not. And so if f is actually an even function, then I find that the Bn is 0. If f is odd, I find that since the sines are odd functions, but the constant and the cosine are not, that a0 is an is equal to 0. And I'm actually going to end up using the theory for an odd function. So let's just save a bit of space here. I have this case. So this is another case which I'm not considering. I'm going to be thinking about an odd periodic function when I get down there at some stage. There are going to be no coefficients. My f function here will be just the Fourier series with the sines in there. So I need to justify why it works at some point, and I'll do that. The more important piece of the Fourier series technology is that I need to be able to calculate the b, and I'm going to be using this. And the b is going to be the integral here of f of x sine of n pi x over L dx. Let's put that on the board now. I've gone slightly over the edge. That's better. Now, in this formula, that was for the full Fourier series, which is going from minus L to plus L. But if f is odd, and I remember that the sine is an odd function, then the combo of two odd functions is an even function, and integrating from minus L to plus L is just the same as going from 0 to L and multiplying by 2. So I can just as well go from 0 to L and multiply by 2. And this will be helpful because when I solve the PDE, this will be where I'm solving the PDE. Okay, so that's the technology from the Fourier series. And I'll use it. I just have to make that justification for why it works at some stage. Okay. Now let me quote to you the problem that I'd like to do. So the PDE example, it's going to be ut is equal to uxx, and that's homogeneous, but I'm going to make it inhomogeneous by adding a 2. Then I'm going to say that at 0 and 1, I have certain boundary conditions on u, and those boundary conditions are that u is 1 at x is equal to 0, and it's equal to minus 1 at x is equal to 1. On top of all of that, I'm going to say that u at t is equal to 0 is going to be some given function f of x, and just by way of example, I will choose x times 1 minus x. So with the 2 there and the 1's there and this particular function here, I ought to be able to go through the whole business, find a general solution and calculate what all of the coefficients are in this general solution based upon this boundary and initial data. So that's the problem. Okay, so now I need to go through step 0 because I've got a 2, 1, minus 1 there. That makes the problem inhomogeneous. So I need to take out those numbers by defining my big U and splitting the little u into the big U plus a new function v. So let's do that. So now I'm going to go through and find the steady state solution. I'll do step 0. Right, so the steady state solution. And it satisfies the differential equation and the boundary conditions with all of the inhomogeneous terms in there. So the only thing that it doesn't have is any dependence upon time. So the steady state solution. So that says that u of x and t becomes big U of x. That means that du by dt goes to 0. uxx becomes u prime primed. And here's my PDE, so that just simply says that u prime primed is equal to minus 2. Integrating twice, I'm going to get that u is equal to alpha x plus beta. The alpha and the beta are just arbitrary constant of integration, minus x squared. Right, so the second derivative of that, these go away, and that gives me minus 2. Right, so that's just integrating this twice, furnishing these constants of integration. And to determine the alpha and the beta here, I need to put in these conditions. So let's do that. So I have to have that u of 0 is equal to 1. So if I put x is equal to 0, I find immediately that beta is 1. And I've got that u of 1 is equal to minus 1. I'm going to need a bit more space here. Let's get down to here. So I'm almost ready to start solving the problem with separation of variables. I just need to figure out what the alpha is and then make the split of the original function u into the steady state solution, which I'm finding in v. So this one tells me that alpha plus beta minus 1 is equal to minus 1. So alpha, since that cancels that, is minus beta. Beta is 1, so alpha is minus 1. So I find that u is equal to beta as 1 minus x squared. That's the steady state solution. Now what I want to do is I want to put little u is equal to this thing plus v of x and t. And that means that ut is just vt, since u is independent of, big U is independent of t. And I need the second derivative with respect to x. So uxx is equal to u prime primed plus vxx. That's just minus 2. So I put that into the PDE at this point, and also the boundary conditions, and at this stage I should have homogenized everything for V. So let's just check that. I have the PDE down there, so that's UT, which is VT, is equal to UXX, which is this thing, U prime prime plus VXX, and then it had that awkward plus 2, but U prime prime is minus 2, so I've homogenized the PDE. Then I have that at x is equal to 0, U, it has to be equal to 1. So now, putting this into there, I find that big U of 1 plus V of 1 and T is equal to 1. But I've applied the condition already that U of 1, sorry, 0. Getting ahead of myself. So, putting x is equal to 0, I've got the big U of 0 plus V at 0 has to equal 1, but I've applied the condition that U at 0 is 1, so that cancels that. And doing the same thing at the other end, I have that U of minus 1 plus V of minus 1 at T is equal to minus 1, but I've applied the condition that big U is minus 1 at 1. Why am I putting minus 1 in there? There we go. So that is the same as this. So my PDE has got no extra term, and my boundary condition is simply that V is 0 at both 0 and 1. So I've now got a nice homogeneous problem for V. Okay, so let's just go over here and record the fact that big U was 1 minus x squared, and I've put U is equal to big U plus V. Right, that's basically all of this slide. So now I've got the homogeneous problem that I can apply separation of variables to for V. So let's do that. It's plain sailing at this point. So I've got Vt is Vxx, V of 0 is V of 1 is equal to 0. That's all of this. Okay, so now let's talk about separation of variables. I need to put V is equal to big X of x and big T of t. That I shove into the PDE. When I do that, I find that I've got x t primed is equal to t x prime primed. The primes here are the derivatives with respect to the arguments, right? So that's a derivative with respect to big T, which is a function of t. That's the time derivative. This is with respect to the argument of x, which is x, so that's 2x derivative. No ambiguity. Let's divide this by the big X and the big T, and I get to this equation which we have encountered before. And the usual strategy is to make that equal to a separation constant and call that separation constant minus lambda. X prime primed plus lambda x is 0. That's what I get from this thing, right? The argument here is that that's a function of t. This is a function of x. I can freeze one independently of the other one. I can look at a fixed position and consider what happens at time, or I can freeze time and think about what happens in x. That means that when I do that, this is a constant, or that's a constant, and so these things can only satisfy this relationship if they're equal to a constant, the separation constant. That's the argument. Function of t is a function of x, only possible if they equal the constant. And we've chosen minus lambda for the reason that we'll talk about in more detail in just a moment. Having set it to be minus lambda, I get this equation for big X, which I'm going to write the solution down as some constant a times the cosine of the square root of lambda x plus the b sine of root lambda x. And just for completeness, that's the equation for big T. So I end up saying that T is something times e to the minus lambda t. Right, so I get sines and cosines in x and in e to the minus lambda t with that choice there. Now the boundary conditions, that's v of 0 and v of 1 better be 0. That translates on this separable form to saying that x of 0 and x of 1 are both 0. So I need to be able to solve this problem and put the function that I'm getting to 0 at two particular points. And I can do that with sines and cosines. Had I made the wrong choice here and put a plus sign there, that would have been a minus sign there. These functions in the solution would have been exponentials. It would have been e to the plus root lambda x and e to the minus root lambda x. And it's not possible to combine those to get the solution to be 0 in two places. So the boundary conditions here would tell you that you have to have a minus sign. The physics of the problem also tells you that when I consider what happens in time, things have to diffuse. This is the heat equation, the diffusion equation. Diffusion smooths things out. Structure goes away. Everything's got to go away. Things end up decaying exponentially. If I'd have got the wrong sign there, things would have grown exponentially in time, which doesn't make physical sense if we're talking about diffusion. Right, so there are various physical reasons why we have a minus sign there, but from a mathematical perspective, separation of variables is really that the only way that you're going to satisfy these two conditions is by choosing the right sign there. Let's carry on. X of 0 is 0. Well, if I just put x is equal to 0, there I get little a. That's got to be 0. So little a is 0, so that means I don't actually have this one. That's constraining the solutions for x. Now let's have a look at the other one. X of 1 is equal to 0. So I'm going to put now b times sine of root lambda equals to 0. If I put b is equal to 0 to satisfy this, I don't get anything there. And at the end of the day, I have to get something. So the trivial solution is not an option. So I cancel the b off, and I need to put the sine of lambda, the square root of lambda, to 0. So this is going to tell me what lambda is. Okay. So here we are. I have the square root of lambda should be n pi, where n is 1, 2, and so on. I could maybe try to put lambda is equal to 0. If lambda was 0, though, that would be 0. I'd just get the trivial solution again. So I don't want that. So lambda is this, n squared pi squared. Ooh, just n squared pi. Okay, so just having a look, I've got that big X, therefore, is some constant b times the sine, and the square root of that is just n pi x, and t is something times the exponential of minus n squared pi squared t. That's solving these ODEs. Those are the solutions, my simple solutions. At this point, I'm just going to have a quick peep over there. So my solutions are sines of n pi x. As I said, we're going to be dealing with odd functions at some point, and for an odd function, the Fourier sine series is sine of n pi x over L. So clearly we're dealing with big L as 1 over here. That's looking ahead. Now, in the scheme of things, when we apply separation of variables, we go through the procedure, we separate the variables, we argue, because we can write the PDE, therefore, as a function of x as a function of t, that we have a separation constant, and the PDE therefore reduces to 2 ODEs. We solve them to get here. There is an infinite number of possible choices for lambda, so we write a general solution, which is that v of x and t is the sum over all of the n's. I have a sine of n pi x. I have an e to the minus n squared pi squared t. And then out front here, I would have this arbitrary constant b times my arbitrary constant here, the happy face. There's no point having the product of two arbitrary functions. I may as well just keep one. And I should choose a different one for each of the n's. So I'll just rewrite that as bn, because we've got a bn over there. All right, so what's the initial condition? So we have to go back to u at this point, because we had the u was equal to f of x at t is equal to 0. And we've got this relationship between u and v. So v at t is equal to 0 is actually u at t is equal to 0 minus the steady state solution. So that is f of x minus big U of x. So I could just call that big F and do things formally from now on. But for the specific example that we've got there, I know that f, little f, is x minus x squared, and that's big U. So minus u is minus 1 plus x squared. Handy cancellation there. So this is 2x minus 1. That's what the initial condition on v is. So I can come back to here to my general solution. I can put t is equal to 0, and then I have to get this Fourier sine series to equal that function. Right? Or more generally, to equal this arbitrary prescribed function. Right? I'm going to be prescribing that. I could say it's just whatever it is and not give a particular example. That would mean that the best I can do is write these down in terms of certain integrals like we have over there. But I'll do those integrals for this specific function here. Okay. So I need that v t is 0, which is what I've called f here. That's actually 2x minus 1 in my specific example, is the sum from n is 1 to infinity of bn sine n pi x. So let's now talk about that mathematical detail, that technicality about why is it that I can do this. How can I achieve this? So this is possible because f is defined on 0 to 1. So therefore I extend f to minus 1 to 1 as an odd function. And I'm free to do that because there's just no information there. I can pick whatever I want. So I'm going to deliberately pick that over minus 1 to 1, I have the odd extension of f. That gives me an odd function between minus 1 and 1. So I'm going to extend f to there as an odd function. and then extend it everywhere else as a periodic function of period 2. Right, I'm dealing with L as 1, and this is for a 2L periodic function. So over here, it's really period 2. Having done that, I can then say, because of the Fourier series theory, so Fourier series theory then establishes that any f of x can be represented as a Fourier sine series. Right, this can indeed be done. Right, so that's the sort of the mathematical detail that establishes that this is a justifiable procedure. However, that's a relatively minor detail as far as writing the analytical solution to the PDE problem down, because I just need to figure out what the B is, and it's given by that. So let's do that. So continuing the words, moreover, the coefficients Bn are given by, right, L is equal to 1. I'm dealing with a big F, not a little f. There it is. So that's the information that comes from Fourier series theory. It establishes that it can be done, and it tells me what the coefficient is. So at that point, this is a formal answer for any old big F, and I have a V, which is the sum over n of the Bn times the sine times the exponential. And that's for V. What about U? Well, U is V plus the steady state solution. Let's just write that as a big U. Right. So this would be the formal solution for any f of x, any initial condition. And bearing in mind that big F is equal to, that's the initial condition on V, that's F minus big U. Right, so that would be the end of the problem. I couldn't go any further if I hadn't have said what that is, but in this particular problem I have said what the little f is, and that translates to the big F being this particular function. So now let's just do the calculation, finding out exactly what the coefficients are. So in other words, let's do that integral. Right. Okay, so with this, I find that Bn is going to equal the integral from 0 to 1 times 2 of that. There's a sign in there, dx, And this is typical at this stage. In order to make any further analytical progress, I have to do this integral, and I have to get a function in there which, when multiplied by a sign, I can integrate. And if this is some sort of a polynomial, you can always do that by integrating by parts. So we just need to integrate by parts. That's a classic textbook example of a problem that you might find on an exam. Okay, so integrating by parts. I have sine, I've got this polynomial. The way to actually deal with this is to end up integrating that and differentiating that, because when I'm differentiating that, ultimately it becomes a constant, and then I can do the final integral. So I'm going to integrate that and differentiate that. So when I integrate by parts, the first thing I get will be this thing times the integral of that. So the integral of a sine gives me a cosine. I have to divide by an n pi, and then the integral of a sine gives me minus a cosine. So that's the first term. Then I subtract off twice the integral. Now I have to differentiate that. That gives us a 2, and I get the integral of that again. So that's what an integration by parts gives me. I can feed in the limits there to give me something. And here, I can just do the integral now, because that's a single cosine. The integral of a cosine gives me a sine. So let's record everything. From here, I'm going to get minus 2 over n pi into, putting the top limit in there, well, that becomes 2 minus 1, 1. And then I get a cosine of n pi. And the cosine of n pi is minus 1 to the n. So this first term, given that I've taken the minus n pi out front here, that's just minus 1 to the n. Now if I put 0 in there, that becomes 0 minus 1, so there's a minus 1, and that becomes plus 1. So because it's the lower limit, there's one minus sign, there's another minus sign from there, that gives us a plus sign, and cosine of 0 is 1. Now this final thing here, that's plus 4 over n pi. Integrating a cosine gives me a sine. There's another n pi. I'm going between 0 and 1. However, I don't even really need to think about this, because if I put 0 in there, I get 0. And if I put 1 in there, I get sine n pi, which is again 0. So that term is actually 0. So I'll get rid of that. I'll get the result here. So Bn is equal to minus 2 over n pi 1 plus minus 1 to the n. Let's just observe that that means that when n is even, minus 1 to an even power is just plus 1. So that's minus 4 over n pi if n is even. If n is odd, this is minus 1, so that's 1 minus 1 is 0. So we get 0 if n is odd. Right, so there it is. So that's how I can express this function f as a Fourier sine series with these coefficients. So at this stage, I can write the solution down for v. However, I may as well skip to the solution for u, because that's really what I wanted. So I've got u of x and t is equal to, right, so there's a big U, there's big U. And then I've got my sum Here's B. So there's a minus sign, so let's just switch the sign out front. Take that into account. So it's 2 over n pi, 1 plus minus 1 to the n. Then I've got the sine of n pi x e to the minus n squared pi squared t. And that's the answer. I could be a little bit more compact in the way that I write the answer, because my sum there has half of the terms being 0. Right? This is really only a sum over the even values of n. So I could just as well write this as 1 minus x squared, and I'm going to sum over n even, just discarding the odd ones. When I discard the odd ones, this coefficient is just 2. So that's one way I could do it. Alternatively, I could write that as a proper sum over a bunch of integers by saying that, well, to guarantee that I have n even here, I could just put n is equal to twice j and let j run over all integers. Oops, I forgot my minus sign there. So it's a sum now, a normal sum over j from 1 to infinity. And wherever I see an n, I'm just going to put 2j now. So this is now 2 over pi j. This becomes sine of 2j pi x. And I've got the exponential. Which becomes minus 4j squared pi squared t. So there it is. Okay. So that's pretty much illustrating all of the material that we need to solve PDEs in Math 256.